A solar eclipse happens when the moon moves directly between the sun and the Earth. When that happens, the moon blocks sunlight from reaching part of the Earth's surface. This is not a random event and it is not mysterious. It is a straight line forming between three objects in space, and that line only lasts for a short window of time. This matters because eclipses get reported constantly, with maps, safety warnings, and travel advisories, and most people have never been told what is actually happening physically. They know something dramatic is scheduled to happen in the sky, but they don't know why it only happens sometimes, why it isn't visible everywhere, or what the difference is between the different types they hear about. This script fixes that. Here's what's actually happening when the sun, moon, and Earth line up. The moon orbits the Earth. The Earth orbits the sun. Most of the time, the moon is above or below the direct line between the sun and the Earth, so its shadow misses our planet entirely and falls into empty space. But on rare occasions, all three line up closely enough that the moon's shadow lands on the Earth's surface. When that shadow touches the ground, you get an eclipse. Think about driving on a highway with a streetlight overhead. Most of the time, other cars around you don't block that light from reaching your windshield. But if a truck pulls directly between you and that light, for a few seconds your windshield goes dark. That is the same basic mechanism, just on a planetary scale, with the sun as the light source, the moon as the truck, and your location on Earth as the windshield. If you understand that one line, you understand the entire foundation of eclipses. The concept in one sentence: a solar eclipse is the moon's shadow landing on Earth because the sun, moon, and Earth have briefly lined up. The moon's shadow is not one uniform shape. It has two separate parts called the umbra and the penumbra. The umbra is the fully dark inner part of the shadow where the sun is completely blocked. The penumbra is the lighter outer part of the shadow where the sun is only partly blocked. This matters because which part of the shadow you are standing in determines what you actually see in the sky. Picture a work light hanging above a job site with a ladder standing underneath it. Directly under the ladder, on the ground, you'll see a small, sharply dark patch where almost no light reaches the ground at all. Around that dark patch, you'll see a wider, fuzzier area where some light still gets through. The sharp dark patch is like the umbra. The fuzzy lighter area is like the penumbra. If your location on Earth falls inside the umbra, you get a full eclipse. If you're in the penumbra, you get a partial one. Stated plainly, the umbra is where the sun is completely covered, and the penumbra is where it is only partly covered. A total eclipse happens when you are standing inside the umbra, the fully dark part of the moon's shadow. From that spot, the moon completely covers the disk of the sun for a short period, usually a few minutes at most. This matters because a total eclipse is the only version where the sky actually goes dark in daytime. Picture someone driving home from work on the day of a total eclipse, not realizing their route runs straight through the path of totality. Within a few minutes, daylight drops to something close to streetlight level darkness, then returns just as quickly. Without knowing this was coming, that sudden shift can genuinely catch a driver off guard. In one sentence, a total eclipse is full daytime darkness for viewers standing inside the moon's darkest shadow. A partial eclipse happens when you are standing in the penumbra instead of the umbra. In this case, the moon covers only part of the sun, and daylight dims somewhat, but never goes fully dark. This matters because most people who say they saw an eclipse actually saw a partial one, not a total one, and the experience is very different. Someone who hears that an eclipse is happening today steps outside without checking their exact location relative to the path and expects the sky to go dark like in photos they've seen, ends up disappointed when the daylight only dims slightly. Stated plainly, a partial eclipse is a dimmer sun, not a dark sky, because only part of the disk gets covered. An annular eclipse happens when the moon lines up correctly, but it is too far away in its orbit at that moment to fully cover the sun. The moon's orbit around Earth is not a perfect circle. It is slightly oval-shaped, so the moon's distance from Earth changes over time. When an eclipse happens while the moon is farther away, it looks smaller in the sky and leaves a visible ring of sunlight around its edge instead of blocking the sun completely. This matters because people confuse this with a total eclipse and expect full darkness that never comes. Someone tuning into a live stream expecting the sky to go black, and instead seeing a glowing ring around a dark center might assume something went wrong with the broadcast, when in fact the eclipse is behaving exactly as predicted for that specific date. In one sentence, an annular eclipse leaves a ring of sunlight visible because the moon is too far away to fully cover the sun. The reason total eclipses are even possible at all comes down to a size and distance coincidence. The sun is enormously larger than the moon, but it is also enormously farther away, and those two facts nearly cancel out. So both objects appear almost exactly the same size in our sky. This matters because without that coincidence, the moon would either be too small to cover the sun at all, or so much larger that it would block it for hours instead of minutes. Picture holding a coin at arm's length in front of a distant street lamp. If you move the coin closer to your eye, a much smaller coin can still block the street lamp completely because the closer object doesn't need to be as large to match the farther one's apparent size. That's why a moon roughly 400 times smaller than the sun can still cover it, because the moon is also roughly 400 times closer. Stated plainly, total eclipses only work because the moon's smaller size and closer distance happen to cancel each other out. Eclipses don't happen every month, even though the moon circles the Earth roughly once a month. This is because the moon's orbital path is tilted about 5 degrees compared to the Earth's path around the sun. Most months, the moon passes above or below the sun's position in the sky instead of directly in front of it. This matters because it explains why eclipses are rare events instead of monthly ones, and why they can be predicted for specific dates rather than expected constantly. Picture two roads that cross each other at a slight angle instead of running side by side. Cars on those two roads only meet each other at the exact intersection point, not everywhere along the route. The moon's tilted path and the sun's path work the same way, only lining up at specific points where the two paths cross. In one sentence, eclipses are rare because the moon's orbit is tilted, so exact alignment with the sun only happens occasionally. Because the moon's shadow is relatively small compared to the size of the Earth, only a narrow strip of land ever experiences a total eclipse for any given event. This narrow strip is called the path of totality. Everywhere outside that path sees a partial eclipse instead, and everywhere far enough away sees nothing at all. This matters directly for anyone planning to view a total eclipse, since being a short distance outside that path changes the entire experience. Picture a spotlight sweeping slowly across a stage floor during a performance. Only the section of floor the beam is currently crossing gets full illumination, while the rest of the stage stays dimly lit around it. The path of totality moves across the Earth's surface the same way the spotlight moves across the floor, only touching a narrow band of ground at any given moment. Stated plainly, the path of totality is the narrow strip of Earth where the moon's darkest shadow actually touches the ground. Because the orbits of the sun, moon, and Earth follow precise repeating physical patterns, scientists can calculate the exact date, time, and location of an eclipse years or even centuries in advance. This matters because it shows that eclipses are not unpredictable events. They are scheduled outcomes of orbital mechanics that can be mapped out with extreme accuracy. Someone using publicly available orbital data to correctly predict the date and viewing location of an eclipse that won't occur for several more years demonstrates that this isn't guesswork. It's calculation. In one sentence, eclipse timing can be predicted precisely because the orbits involved follow fixed, repeating patterns. Looking directly at the sun during an eclipse is dangerous for the same reason looking at the sun on a normal day is dangerous. The sun constantly sends out radiation strong enough to damage the light-sensitive tissue at the back of your eye, and that danger doesn't disappear just because part of the sun's disk is blocked. This matters because a partially blocked sun can look dim enough to seem safe to view directly, even though the exposed portion is still emitting the same intensity of radiation as always. Picture a bulb on a dimmer switch that has been turned down partway. The bulb looks less bright, but if you touched the exposed filament, it would still burn you, because reducing how something looks doesn't reduce what it's actually doing. That's why proper eclipse glasses, not sunglasses or homemade filters, are required for direct viewing at any point except the brief seconds of full totality. Stated plainly, partial coverage of the sun does not reduce the danger of looking at it directly. Here's what people most often get wrong. A common mistake is assuming an eclipse can happen at any new moon, since a new moon is when the moon sits between the Earth and Sun each month. This confusion comes from not knowing about the 5-degree tilt in the moon's orbit, so most new moons pass above or below the sun instead of in front of it. The fix is remembering that alignment requires the moon to cross the sun's exact path, not just be in the same general direction. Another common mistake is assuming any eclipse means the sky goes fully dark, when in fact most eclipse events people witness are partial ones with only mild dimming. This confusion comes from photos and footage of total eclipses circulating far more widely than partial ones, giving a skewed impression of what's typical. The fix is checking specifically whether a location falls inside the path of totality before expecting full darkness. A third mistake is assuming eclipse glasses become unnecessary once the sun looks mostly covered, which comes from treating visible dimness as a stand-in for actual safety. The fix is remembering that the radiation danger stays constant regardless of how dim the sun appears, right up until the moment of full totality. A fourth mistake is assuming an entire country or hemisphere experiences totality together, when in reality the path is only a narrow band a few hundred kilometers wide. This confusion comes from not grasping how small the moon's shadow actually is compared to the size of the Earth. The fix is checking an actual path map rather than assuming proximity to the general region is enough. Let me show you exactly how this works when someone actually plans to view a total eclipse. Say a person hears a total eclipse is coming through their part of the country in a few months. First, they need to find the actual path of totality, because their town being in the same state as the eclipse doesn't mean it's in the narrow strip where the moon's darkest shadow will fall. Second, they check the predicted date and time, trusting that the calculation is accurate because eclipse timing follows fixed orbital mechanics that have already been mapped out years in advance. Third, once they confirm they're either inside the path or need to travel a short distance to get inside it, they buy certified eclipse glasses ahead of time because the danger of looking at the sun directly doesn't go away just because part of it will be covered. Fourth, on the day itself, if their exact spot ends up slightly outside the narrow path, they experience a partial eclipse instead of totality, meaning the sky dims but never goes fully dark, which is the direct result of standing in the penumbra instead of the umbra. Every part of that day, from planning the trip to protecting their eyes to understanding what they actually see in the sky, comes directly from the same handful of concepts working together in sequence. There are practical situations where this understanding has a real cost attached if you get it wrong. Deciding whether to travel to a path of totality location only makes sense once you know the difference between total and partial coverage, since a long trip aimed at the wrong location wastes both time and money for an experience you could have gotten closer to home. Buying certified eclipse glasses ahead of time avoids the risk of permanent eye damage that comes from improvising with sunglasses or unfiltered devices during the exposed portions of the event. Knowing that a scheduled outdoor task involving solar power, such as calibrating panels or running light-dependent equipment, will see a brief, predictable drop during an eclipse prevents someone from wasting time troubleshooting equipment that isn't actually broken. Reading an eclipse map correctly and understanding the difference between an annular and a total event prevents the disappointment of expecting full darkness and getting a bright ring of light instead. You can now explain in a single sentence why a solar eclipse happens and why it doesn't happen every month. You can now tell the difference between a total, partial, and annular eclipse just from a description or a photo without confusing one for another. You can now check whether a specific location falls inside a path of totality and understand what that actually means for what you'll see and how you need to protect your eyes. You can now explain why eclipse dates are published years in advance, because you understand this comes from fixed, calculable orbital mechanics rather than guesswork. This is the understanding you should have gotten the first time this topic came up, and now you have it.